Well, let's get started in chapter 4. We're going to learn about some triangle stuff. We're going to learn about proving triangles are congruent. Lots of fun stuff in chapter 4. Oh, that's my coffee machine. Don't worry about it. Okay, so you probably already know the triangle sum. You know, all the angles in a triangle add up to be 180 degrees. Well, we're going to actually prove that today, and we're going to look at some other stuff as well. So lesson 4.1. So our objective today is for students to be able to classify triangles and find their measures and their angles. How can you find the measure of the third angle of a triangle if you know the measure of the other two? Well, that'll actually be a simple problem. Just add and subtract wherever needed. But we'll also be looking at the distance formula again in this chapter. So let's take a look. So we can classify triangles two different ways. One way is by their sides. If none of the sides are congruent, we say it's scalene. That's this word here, scalene. And if two of the sides are congruent, we say it's isosceles. It's kind of tricky to spell the first time. And if all three sides are congruent, we say it's equilateral. Take a look at that word there real quick. It's pretty easy. Whoops. Let's take a look here. If you look at this word here real quick, equi means what? Equals. And what's this lateral part? That means side. Okay? And so this word should be pretty easy to figure out. Equilateral, equal sides. You've heard of a lateral pass in football. Well, that's sort of where the quarterback passes to the sidelines. Or to the side, kind of. Well, anyhow, we have other ways we could classify triangles. That's also by their angles. If none of the angles are bigger than 90, this is less than 90 degrees, okay, we say that the triangle is acute. If they have an angle that's exactly 90, that all of a sudden becomes a special triangle. That's probably the most abundant ones in our society. It's the right triangle. And you could always tell that you have a right triangle because they will have that symbol right there. And if you have an angle that's above 90 degrees, then automatically it becomes an obtuse triangle. Okay, that angle right there is more than 90. And if all the three angles are the same, kind of like this scenario up here, we will say it's equiangular. Well, how about that? That shouldn't surprise you. Equi again means like equal, and then angular, equal angles. Okay, so if you have equal angles, you have equiangular. So there's two ways we're going to be describing triangles. We can describe them by their sides, and we can also describe them by their angles. So let's take a look here. Now, to describe them by their sides, this can kind of be annoying sometimes because sometimes you have to do the distance formula. And I don't know if you remember the distance formula, but let's write it down again. The distance formula we'll use over and over again. We've used it in last chapter already. It's x2 minus x1, and then you take that quantity, square it, and you add that to y2 minus y1, and you take that quantity and square it. And it really doesn't matter which point is the first one and which one's the second one. So sometimes we can determine the lengths of all the sides and find out if it's isosceles. And it may turn out that this side is congruent to this side. Then we have an isosceles triangle. What we cannot do is just say oh well, it looks like the sides are all different, so it's scaling. Well, in this chapter, in chapter 4 here, this first section, we have to determine the lengths by using the distance formula. And so after we do that, we'll know for sure what the lengths are, and then we don't have to guess. The other thing we want to do is determine something about the angles if it's a right triangle. Now, to answer this part, what we will do is look at slopes. Okay, we will look at the slope. Okay, and we suspect that there might be a right angle right there. Okay, so we'll look at the slope of this segment, and then we'll look at the slope of that segment. And remember, if slope number 1 times slope number 2 is equal to -1, then that would mean that we have perpendicular lines, or perpendicular slopes. And that's how we could check to see if we have a right triangle. So the first thing we'll do is classify this by its side, so we have to determine all the distances. So distance number 1. Well, we may as well start off with this one. This one we'll call number 1, this one we'll call number 2, distance number 3. And it's just a matter of plugging in the points and putting them in the formula. So let's take a look at what our formula tells us to do. Switch to black here. It says to subtract the x coordinates, so we just subtract those 2 coordinates, and then we subtract those 2 coordinates. Alright, and then we square them. We take the square root, pardon me. Alright, so -1 minus 0, we take that quantity and we square it, plus we do this one now, 2 minus 0, we take that quantity and square it, and we just work horizontally. Of course, -1 minus 0 is -1, and so that's just -1, but then you square it, so it'd be like -1 times -1, and of course -1 times -1 is just 1, so that's 1. And then here 2 minus 0 is just 2, and then 2 squared is 4. Alright, and so this whole distance here is equal to the square root of 5. Now, you don't have to find the exact answer with a calculator. We can leave our answer in terms of square roots. All we're really after is to determine the 3 lengths and determine whether they're the same or not. Well, so we found distance number 1, and now we can repeat the process, find distance number 2. That's this, and I'm going to go ahead and do this one right here. So once again, you just subtract the coordinates, the x coordinates. So that's going to be 6 minus a minus, well, it's 6 minus a minus 1, right? Oh god, that's ugly. Let me rewrite this. Come on. 6 minus a minus 1. And we're going to take that whole quantity and square it. And we're going to add that to the other difference. We have to subtract the y's. So we subtracted the x's, and now we need to subtract the y's. Okay, so that's going to be 3 minus 2, and we square that. And as you can see, that's getting a little messy, so I'm going to erase some of this junk. Bam. Okay, so again, we found out that one was square root 5. That was the first one. Now we're finding this length up here. Erase this now. Okay, so let's just simplify this. 6 minus a minus is actually a plus 1 here, so it's 6 plus 1, so it's 7. And then 7 squared is 49. And 7 times 7, right? That's that first one. And then 3 minus 2, of course, is just 1. And then 1 squared is 1. And so this time we get the square root of 50. And again, we don't have to find the exact answer here. This answer is okay. Square root of 50 is square root of 5. Obviously, these two lengths are not the same. So that's the square root of 50. Alright, well now we're after the third length. Maybe I can use a different color again. We're after this third length over here now. And so we'll just go ahead and do it. Now, by the way, I agree that this triangle looks fairly obvious that it's scaling. But on your assignment and also on the test on this chapter, you're going to have to justify your answer by finding the three distances. So you may as well get used to this formula. You're going to be using it quite a bit. So let's see here. We've got to subtract the x coordinates. That means we subtract the 6 from that. Okay. So 6 minus 0. And we square that. Plus, when we take this y coordinate and subtract the other y coordinate, 3 minus 0. And we're going to square that. And of course, 6 minus 0 is a 6, and so 6 squared is equal to 36. And then 3 minus 0, of course, is 3, and then 3 squared is 9. And so that's equal to the square root of 45. And as you can see, none of these distances are identical. And so the conclusion that can be made, since all three lengths are different, we're going to say that this is a scalene triangle. Scalene. Okay. Well, now there's this matter of determining whether it's a right triangle. So, to do that, like I said, we're going to look at the two slopes. And so let me just erase some junk so I have more room to work. And so let's find out slopes now. Slope number 1. Now, by the way, there's only one spot that we even suspect right angle. It's right here. So we won't check it. We won't check the slopes for that angle, and we won't check for that angle either. We'll just, the natural choice is right here. Okay, so slope. Remember, it's the slope formula, in case you forgot. It's y2 minus y1 over x2 minus x1. Remember, it's rise over run. Over run. And sometimes you can just look at the diagram itself. I mean, if they've drawn the diagram on here, you can just get the rise of the run from the diagram. I mean, just look at it. I mean, let me show you how this works. You go down 2, right? You go down 2. So the rise portion is negative 2. And then you go from this point over to here. Okay? So the run part is positive 1. So the slope is equal to negative 2. Alright? That's easy enough. Okay, that being said, you could have also done it by subtracting the coordinates, and you would have gotten, in this case, you would have gotten 2 minus 0 over minus 1 minus 0, which equals 2 over negative 1, which equals negative 2. You see? So if you would have used the formula here, you would have gotten the same answer in a slightly different way. Okay, but that being said, the diagram is drawn on a grid here, so we may as well just use the grid to our advantage and calculate the slopes directly. So the slope number 2, we're going from this point clear up to here. So how far do we rise? We go up this way. I'm going to do the rise part first. 1, 2, 3. We go up 3. Okay, and how far do we run? Okay, well, we'll go over 1, 2, 3, 4, 5, 6. Number 6. Okay. Well, that, as you know, this fraction does reduce because that's 3 times 1, and this is 3 times 2, so there's a common factor of 3 there. So this gives you 1/2. Well, and as we might imagine, slope number 1 times slope number 2 does equal -1. I mean, take a look here. We have -2, okay, times 1/2. Well, 1/2 of 2 is 1, and of course this negative makes it a -1. And you should have recognized that this was the case, because remember, anytime you have perpendicular slopes, you're going to have reciprocals, where this is a fraction here and you can just flip it. So, and that's the case here. So remember, to get the -1, one of these has to be positive, one of them has to be negative. So there you have it. We can make the full conclusion now on this triangle. We can classify the triangle by its number of sides and also by its angles. Okay, so the final conclusion we would have for this triangle right here, we would say it's a scalene right triangle. Scalene means that none of the sides are the same. Right triangle means that there is a right angle in here. And so that's how we would describe this. Now, if you want to call it a right scalene triangle, like you can switch these two words around, that's fine. No big deal. Doesn't really matter which word goes first. Anyhow, that's how we do these problems. So quite a bit of work for one problem, right? You got to find the distance formula 3 times, and so this assignment might be annoying for a while, but that's why there's only a couple of those problems on this assignment. Now let's take a break while I get my coffee here for a second. Okay, so let's continue. And then there you saw it. Those were the three distance formulas we did. We did the slopes. There you have it. Alright, so now you're going to try it. Well, I don't want to waste our time on the Camtasia video doing this again, but maybe we could have a couple students do this one on the board, where we find the distance number 1, and then we can find distance number 2 and distance number 3. So classify it by its sides and by its angles. So once again, what we would be doing is the distance formula, and that's equal to this ugliness, x2 minus x1. You take that quantity and you square it, and then you add it to the quantity y2 minus y1, and you square that quantity. And usually you can leave your answers in terms of square roots. If you want to, you could use a calculator and find the exact answer. Just be careful putting this all in your calculator. A lot of people make mistakes. So then what you're going to do is find distance 1, distance 2, distance 3. Okay. Then you're going to find slope number 1, slope number 2. And you could just check and see this product here. If slope number 1 times slope number 2 is equal to -1, then that would mean that we have a right triangle. It means they're perpendicular segments, and so that we'd have a right triangle. Now it seems like the only place that would be possible would be this spot right here. That obviously is not a right triangle. That obviously is not a right triangle here. So don't worry about this spot and this spot, those two angles. But this might be a right triangle up there. So I'll let you do that. We can do it together as a class, but those problems take a while. So, and we just did one, so let's skip this and go on. Okay. Well, we're going to get a couple theorems. One about the interior angles of a triangle and one about the exterior angles of the triangle. So take a quick look at these pictures here. these red angles, the little shading right here, show you the interior angles. And let me just review an idea about interior that we've had before. If you take any point on this segment, any point on this segment, and you connect them, remember, that's how we determine the interior for an angle. Okay, we took 1 point from one ray and 1 point from another ray. Well, you can use that idea here. You take any point here, you connect them, and that whole segment would be on the interior. And so you got all these segments that you could connect, and all these different dots you could connect. And so that idea of interior is repeated here. Naturally, the part that's not on the interior is called the exterior. So one thing you should realize is that if this is your interior angle right here, the exterior angle, you could make a straight line. You see, there's always a linear pair involved. That's what I want you to notice, is that there's a linear pair. So for example, if this angle here were 30 degrees, you could automatically figure out this one because it's a linear pair. It's 150 degrees. Okay, now it doesn't matter if you're looking at this exterior angle made by this linear pair. There's a linear pair over here also. These two angles make up a linear pair. You see, there's a straight line. But either way, this exterior angle would be exactly the same. So regardless of which exterior angle you look at for this interior angle, the two exterior angles are going to be the same. So hopefully you can see that by my excellent illustration here. Yes. Okay. Well, so we have a theorem. The sum of the measures of the interior angles of a triangle is 180 degrees. This is actually an easy theorem to prove, and we're going to prove it in the next slide. So let's take a look. To prove certain theorems, you may need to add an auxiliary line. An auxiliary line is like an extra ray or an extra segment or whatever. And I want to give you the idea behind the proof. So let me just start. Before we look at the proof, here's the idea. We were told a while ago that if you had a line sitting there, okay, you can pick 2 points here. Alright. And we learned way back in chapter 1, through any 2 points there's exactly one line. Okay, so imagine this is a straight line. Alright, now we also learned a while back that through any line, well, there could be a point that's not on the line. Okay, so here's a point out here. Here's a point P. How many parallel lines can we draw parallel to this given line that passes through this point P? Well, hopefully you would all agree that there's one. And it's true. There is one. And so there's one line that's parallel to the given line. So that this line is parallel to this line. Okay. Well, now you notice that we could create a triangle. Okay. So there's our triangle like that. Okay. So here's angles 1, 2, 3. Okay, so now we're going to add in just a couple other angles here. 4 and 5. Now, one thing you should notice is that this group of angles up here create a straight line. So what I do know then is that angles 4 plus angle 2 plus angle 5, they create a straight line. So it's kind of that linear pair idea, creates a straight angle. So what we're going to say is that that straight angle adds up to be 180 degrees. Okay, but guess what? You'll notice a zigzag pattern. Since we have parallel lines, we have alternate interior angles. So there's this zigzag pattern, right? You see the zigzag? There's a zigzag pattern, right? So what it means is that this angle here is congruent to this one because alternate interior angles are congruent. Well, what that means is that we could replace angle 4 with angle 1. And you'll notice that there's a zigzag pattern over here as well. There's a zigzag right here. Okay, I should have done it in a different color, and I'm not that great with my pen, as you can see. But what it means is that this angle here is congruent to this angle up here. And what that means is we could replace angle 5 with angle 3. And there you have it. The three angles in a triangle all of a sudden equal 180. And that's really all there is to the proof. So let's take a look now a little bit more formally what we have. So draw BD parallel to AC, and we'll just say I wonder, hang on just a second, whoops, let me go back. We can say that's an auxiliary line. Alright, auxiliary line. So what it means is that you start off with a triangle like this. Okay. So A is here, C is here, and B is up here. Okay, so there's this point B. Now it says draw BD parallel to AC. So we have a parallel line. Okay, we're allowed to do that because there's that theorem that says through a point not on the given line there's exactly one parallel line. So this is our parallel line BD. So that's that part. This is our auxiliary line. Okay. Now, let's just put the angles in here. We're going to put angles 1, 2, 3, put 4 here, 5. You see, so angles 4, 2, and 5, they add up to be 180. Why? Because we have a straight angle. We have a straight angle. Right here, those three angles together have to add up to be 180. Because it's a straight line. Okay, so then what we say, because of the parallel lines, we were told that we have parallel lines right here. You see? So if we were to continue this, these lines are parallel, these two. And so once again we have this zigzag pattern. And so since you have the zigzag pattern right here, okay, angle 1 is congruent to angle 4. Okay? And so that's what we're saying here. And likewise, you could say angle 3 over here is congruent to angle 5 because there's a zigzag pattern on this side. Okay? Alright, so anytime you have this zigzag pattern, you're going to have alternate interior angles. So the reason that we can say that these two angles here are congruent is the alternate interior angles theorem. And so now what we're going to do is substitute right here and take this angle, substitute right there. So that way we're going to say angle 1 plus angle 2 plus angle 3 is equal to 180. And that's just called substitution. Property. Now, by the way, technically I should have these little bitty m's in here because we're talking about the measure of each of these angles. Okay, so the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. Alright, I think that's kind of ticky-tack, but oh well. But there you have it. That's what we were trying to prove, so we're done. We're trying to prove this. So now we know for any triangle, no matter whether it's a right triangle, obtuse, acute triangle, doesn't matter, the sum of those three angles on the interior will always add up to be 180 degrees. And we're done with that. So here's another new theorem. This one says, well, first of all, it has a new name. It's called the exterior angle theorem. So there's an exterior angle, and it turns out that there's three angles in here. You have three interior ones, right? It turns out that this one's equal to the sum of these two angles added together. You add this one and this one, and you just add them together. So how do you describe these two angles over here, though? That's the tricky part. And so this is how we say it. The exterior angle, that's referring to this one right here. Okay, this exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent. Alright, remember adjacent means next to. In other words, it's a neighboring angle. Well, the angle that's adjacent to this one is this angle over here. These two angles would be adjacent. So as far as this exterior angle is, thinking, these two angles over here are not adjacent with this one. So that's what they mean, the two non-adjacent ones. So there's our little bitty theorem. It says that this one's equal to these two added together. All you need to do is add those two angles together. And this turns out to be a real easy proof because we just set up a couple equations. Like, for example, we now know that angle A plus angle B plus angle C is equal to 180, right? Pretty easy. Because that's the triangle sum theorem that we just proved, right? And we just proved that on the previous slide. But what else do we know? We know that there is a linear pair right here. There's a straight angle from here to here. So there is a linear pair, and you can see there's a line right here. So we could also say that angle 1 plus angle C is equal to 180. Okay. Well, if this side here is equal to 180, then can't I take this and shove it in right there? And they're both equal to 180. So that is, in fact, what we do next. We say angle A plus angle B plus angle C. Oh, let's write that as pay attention. Okay, so we have angle C is equal to angle 1 plus angle C. And notice what we have here. We have on both sides of the equal sign, we have an angle C. So since we have an equal sign here, I can use the subtraction property of equality. So I could subtract angle C here, and I could subtract off angle C here. And what's that give me? It gives me angle A plus angle B is equal to angle 1. And that's what we were trying to show. I mean, think about it. That's what we're trying to show, that angle 1 is equal to angle A plus angle B. So there you have that theorem. It's a pretty easy idea. Well, now let's try a problem now. I think the main issue that students have with this is they don't recognize when the scenario comes up. And so they're looking at this and they're asked us to solve for x or find the measure of JKM or blah 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 blah. And we look at it and go, okay, I see an x, I see a 70, I see blah blah blah. Okay, so they don't realize on this particular problem, hey, you're supposed to use this idea right there. Now, how do you recognize it? Well, first of all, there's an exterior angle. Do you see the exterior? There's an exterior angle right there, you see? Oh. Well, the theorem that we just read says that this angle here must equal the sum of those two. So that's a pretty easy equation to deal with then. So we're going to take 2x minus 5. We're going to say it's equal to the sum of these two. So it's x plus 70. And now you just rely on your baby algebra skills and solve this equation. So we could subtract x here because we have an equal sign. We can use the subtraction. Well, we want to subtract x here. And at the same time, we can use the addition property to get rid of this 5. I'm going to get rid of the 5 and do this all in one step. How about that? 2x minus x is 1x. Okay? And then these x's are gone. These 5's are gone. 70 plus 5 is 75. Alright, so we're thinking that we're done. But only a bozo does that. Okay? We did find the value of x, but that's not what we're after. We're after the angle JKM. JKM is this angle right here, right there. So we need to figure out that angle. So we're going to plug that in for x right here. 2 times 75 and then subtract 5. Well, I think that's 150. Subtract 5, we get 145 degrees. So that's going to be equal to the measure of angle JKM. Okay, so there's where we finish things up. Now keep in mind, this always comes up on tests, comes up on assignments, where part of your job is to pay attention to what you're being asked and seeing if you can follow directions. So make sure you complete the problem completely. Alright, so here's another problem. You can try it now. Once again, you have the exterior angle right here. Okay, so it has to be equal to these two added together, because here's the exterior angle, here's its neighbor, this one's the adjacent one, so we wouldn't use this angle. We have to use the two far away ones. Alright, so what we're going to say then is that 3x plus 6 is equal to 80 plus x. And maybe a student can finish this for me. Whoops. 3x plus 6 is equal to 80 plus x. So a student can wrap this up for me. I'm going to move the x's over, move the 6 over, and do some basic algebra. Okay, for our Camtasia lesson, we're just going to continue. So I'm pretty much done. How can you find the measure of the third angle of a triangle if you know the measure of the other two angles? Well, just use the triangle sum theorem. You know they have to all add up to be 180, so you can add up the first two angles and subtract from 180. And so it's pretty easy. But the first part of the lesson, remember, it had to do with classifying triangles. And classified them two ways, by doing the sides, and then we also talked about the angles. Remember, the sides involved the distance formula equal to that ugly square root thingy. And remember, for angles, it could be a right triangle, it could be an acute triangle, it can be an obtuse triangle, and so on and so forth. A lot of good stuff in this first lesson. And so now we're ready to stop. We'll continue tomorrow with 4.2.